we study divergence theorem. The vector field is given in here. Divergence, definition of divergence is partial derivative of x component with respect to x, y component with respect to y, z component with respect to z, and add them all. That's it. So there is a scalar product. So this is, if you write down the gradient operator, it is so xyz component is the operator is applied to x component of the vector, y component, z component separately. Okay. Divergence x is x, y, z, x derivative with respect to x, x2, x2, x3, x3. So it is a 1, 1, 1, 3. Current density of a mass flow. Current density is defined by rho times v, and rho is the density and v is the velocity. So if you integrate this current density over a surface, then you will obtain current. Usually we learn current for the charged particle, but we can also define the current density and current for mass. Just replace charge Q with mass. Because it is in general, the current density varies depending on the position and time. So current density J, density rho, and velocity v, all of them depends on time and position. Find the integral showing the time rate of change in the mass inside the closed surface S. There is a closed surface, and closed surface can be divided into many pieces. So we have the sigma, that is the area of the tiny patch, and this sigma is a vector. It is a product of area multiplied by the unit normal vector that is perpendicular to this surface. We will find it can be used to find the mass flow, but before we go ahead, there is another way to compute the mass inside the closed path. Mass is, if it is uniform, rho equals mass over volume. If it is very tiny, then small mass is density multiplied by volume. And this volume can be expressed as a product of dx, dy, dz. So rho, this one. This is compactly expressed as a d cube x, volume element, multiplied by density. Because density is a function of time and position, so we have included the argument. So if we integrate over the volume, whose boundary is this closed surface, then we integrate this one over V to find the total mass. If I want to compute the time derivative, then I can take the total time derivative operator in here. So why don't we compute delta M? Delta M, there's a change of mass inside this closed surface during the time interval from t to t plus delta t. Here, if I think about a flow of mass passing through this surface, this is a surface, and this is cross-sectional area, and during delta t, there is a motion by delta x equals v delta t. So mass flow comes out of the surface to this direction. Okay? Then during delta t, because there is a cross-sectional area d sigma, the volume that passes through this cross-sectional area d sigma during delta t is d sigma perpendicular direction v delta t. So delta v equals delta v equals d sigma v delta t. The reason why I put the negative sign on it is that the reason is that if mass inside this volume penetrate this surface to go out, then what happens? The mass inside decreases. So if the mass passes through the surface from inside to outside, then the amount of mass is positive. This mass, volume multiplied by density, this is a positive. However, the amount of charge that has passed through the surface has disappeared inside. So the mass inside must decrease. So delta m is negative, but this amount is positive. So to fix this error, I put the negative sign on it. Next, what is the volume? This volume element, this sigma is the cross-sectional area, and this is a vector. It has a direction perpendicular to this surface from inside to outside. So velocity, if a flow is not perpendicular to this normal direction, there is a factor of cosine theta. For example, the plate, this area is in this direction, and flow is parallel to this surface, then cosine half of theta equals 0. That means it does not change the mass. It does not make any mass change. So there is a cosine theta dependence because of the scalar product between the normal vector and velocity. So there is a scalar product. And during the time, delta t. Okay, so this is the volume. Volume is multiplied, density is multiplied, and sum them all. If you make this delta and delta t very tiny, then this sum becomes an integral. This rho inside of delta v, there is a v and d sigma delta t here, and integrated over surface. And there is a circle. This circle means the surface is closed. Closed surface. Closed surface S. Okay. If this integral is positive, then mass has been flowed out. So the inside mass is defined by capital M. The capital M decreases. So I have to put negative sign to make this one is a positive if mass flows out of the surface. Okay, this is called the continuity equation. And we take the limit as delta t goes to 0. Then we can divide both sides to make this one time derivative of total mass inside the closed surface is the integral of this sigma dot rho v is equal rho v. Rho v is defined by the current density. So current density dot infinitesimal surface area vector integrated over the closed surface. And then we make use of divergence theorem. Any vector surface integral of a scalar product over a closed surface is identical to the volume integral over the volume whose boundary is the surface. So over the volume enclosed by the surface. And this current J dot d sigma over the surface is replaced with the volume integral. So this is a 2D integral, this is a 3D integral, right? So because we have increased the number of integration, there must be a differentiation. That is the divergence. Okay, so 2D integral becomes a 3D integral over volume. So we have a dimension, length dimension negative is necessary. That comes from this derivative. So divergence J's volume integral is always the same as current density's surface integral over a closed surface. We make use of this. Then this one can be replaced with divergence J's volume integral. In addition, mass is the density integrated over the volume. Therefore, mass is the density multiplied by tiny volume integrated over V. All right, this is a volume integral, this is a volume integral. Therefore, left-hand side becomes this, and right-hand side has been transformed into a volume integral using divergence theorem. So compare this. So we don't need this one anymore. Compare these two. I have a time derivative outside of integral, and this integral is over volume instead of time. So this integral, when we evaluate this integral, time is fixed. However, I would like to change the time. That means before we carry out the integration over x, that means we fix x the same. However, we vary time in this row. So now we can express this one as the partial time derivative instead of total time derivative. And then move this one to the right-hand side and exchange left and right. We find the divergence J plus this one negative is replaced with positive plus density's time derivatives volume integral must be 0. And this one is whatever volume. I'm interested in the point at a single point. For example, x 0. And I would like to enclose this point by a very tiny volume, that is delta V. So I'd like to make this one very, very small. What happens? For example, I want to integrate x over 1 to 1 plus epsilon dx. What happens? And epsilon goes to 0. What happens? It is very, very close to 1. So it is something like I can approximate. So we 1, 1, 2, 1 plus epsilon dx. So this is something like epsilon. Aha. If the lower limit and upper limit of an integral collapses to a single point, virtually the same point, then integrand becomes a constant. That means if delta V is shrunken into a point flight, but not exactly a point, but infinitesimal region, then this integrand becomes constant. It can be factored out independent of this integral variable. So it is pulled out of the integral. It is a very tiny, this volume is a very, very tiny if the volume is a scale epsilon cube. However, it is not 0. We take the limit as epsilon goes to 0, but limit does not mean we substitute epsilon is exact 0. So product is a 0, the tiny number, constant, this constant must be exactly 0 because this relation is for any kind of volume. Therefore, we conclude that divergence J plus time derivative of density is always 0. Sometimes we can write divergence J equals this. This is the differential form of continuity equation. This is true for massive flow, and it is also true for charged flow.